I'm certain that we don't currently have a proper like mathematical basis to talk about all of the components orthogonally. So I'm using basis like in a sense that I'm borrowing from like linear algebra, right? In a basis, if you have a good orthogonal basis, then all of the elements of your space are orthogonal to each. Sorry, all of the elements are a linear combination of these orthogonal things, these orthogonal elements. And typical, linear algebra. Like the point is, once you have it that way, you can very precisely and easily communicate ideas, in my opinion, because you know what everything's talking about. I don't think we're yet in that situation with the Wikipedia article on neuro-symbolic AI. I like the dichotomy here. Like, I think these two have a sense in which they're like orthogonal, and I think that's embodied in the notation. And I think, yeah, I think this says these categories are not exhaustive, as they do not consider multi-agent systems. However, I think there is another sense in which they're not exhaustive, which is, well, first off, you don't have all the combinations here. And in fact, I was able to notate some that I think have intuitive definitions, but those definitions are my own. I made them up, and it's not represented here, nor is it represented like here. It's possible, like I didn't look that, like I didn't read the paper like that deeply. It's possible this is covered somewhere, but right now my pickle is that we don't have a basis yet, and currently I'm working towards a basis, and I'm going to explain how I know that there are at least 3 different dimensions. I know that there are at least 3 different dimensions because this one is synthetic data. So it's got a neural and neural caller-callee relationship. So but the example is training a neural network to do symbolic actions, to perform symbolic computation. And first off, I think that's a really interesting thing, period. But I also like so okay, but before I get ahead of myself, I know that training data is involved, and actually the training data in this case is generated training data. So let me give a citation for that. Yeah, right there. So train a neural model for symbolic computation by using a system to create or label examples. So you're compiling down discrete stuff. You're compiling down symbolic stuff into data that you're using the neural network to train on. I just think that's, first off, like a really interesting idea. I don't see that represented in the research that often. But also, it's orthogonal to everything we talked about so far because it does consider training data. So I would have to add a whole training data column. But this is a table about control flow, so I didn't quite add that yet. But that's how I know there needs to be like a training data column, because symbolic systems, I guess these aren't trained at all. So they're fixed, they're hard-coded, they're static. And then you can evolve the systems over time using like a genetic algorithm. So that's yet another dimension that's possibly in there. But before we even get there, we already don't have a basis, because so we have inputs and outputs represented by inputs and outputs. I think I meant to write caller and callee. He who does the calling and he who is called. And dominant computation mode is just the best way the best way I was able to represent this idea that that all of these systems have aspects of themselves which are symbolic, just because there's an outer control loop that does things. Like for example, with let's look at this example. A ChatGPT calls a calculator. So in this example, what you actually end up with is ChatGPT is calling a calculator, but ChatGPT contains whoops, let's see, is that right? Yes, okay. ChatGPT is this one and this one. Okay, great. So yes, okay. So that's what I meant by symbolic evaluation engine. Is I mean like this will evaluate the mathematical expression that ChatGPT says to evaluate. And there's like an outer loop, because during the generation process, there's some form of an outer loop that is waiting for you to output stuff like a calculator thing, like a calculator call, like a function call. And then you like, just using that, you substitute the result and then append it. So basically, dominant computation mode refers to the fact that like at the end of the day, there's a symbolic algorithm. There's a discrete algorithm that a programmer wrote that is actually controlling the underlying flow of control. So it's kind of like this meta point that we just kind of like admit off the face of it that there is a there's a human written control loop in all of these systems. So when I say dominant computation mode, I just mean like the thing that's most interesting, the thing we're really talking about. Like in ChatGPT, like even though there are loops upon loops that are written by humans, right? The dominant computation mode would refer to the fact that you have a large language model that takes in strings, it tokenizes them, right? And then it produces the probability of the next token. That's it. And then we use beam search across that. I don't know, maybe ChatGPT in particular uses greedy decoding instead of beam search, but the point stands is you can do beam search, and you return the next token, okay, and then the generation itself bakes in one of those like beam search terms, and you also have this like symbolic system that can take, it's a calculator. It can take hard facts and like hard inputs, discrete inputs, exact inputs, right? And output discrete outputs. Okay, good. So the problem here is that this problem has more dimensions than we've acknowledged yet, because there are even systems where you bake in hard rules, discrete rules into neural networks, and the neural networks just follow those discrete rules perfectly, and they didn't actually have to learn them, but the model, that paradigm is basically no different from a function call, except the function call would happen by, activating particular neurons. And even if you embed that algorithm into the network has to learn it. The network has to learn how to use that particular sub network. And all of that is true as long as the system contains more learnable parameters. So what I'm trying to figure out is, like, how do you even talk about this kind of stuff such that you have a bunch of columns, and then you have a bunch of like elements that can fall into those columns, such that you specify each of those elements, and then that uniquely identifies a single point, a single one of these types of neuro-symbolic AI. Because it can be argued that every single form of neural networks are neuro-symbolic in some sense. And in fact, the Wikipedia page says that even like Roberta, GPT-3, subword tokens, because technically subword tokens are discrete. So language models are taking discrete input. So actually, maybe that's why I had input and output here. Maybe we need call he, input, output. Maybe this takes us a little bit more towards the goal, a little bit closer to the goal. But again, I don't know. And the last thing that's worth exploring here is the symbolic square bracket neural paradigm, which is it's what AlphaGo uses. It's just tree search. And you have a neural evaluation engine, and it's just tree search. It's just depth first search or breadth first search. That's it. And I think that's a beautiful paradigm. I think it's truly beautiful and poetic, because compared to language models, it's less likely to, it doesn't suffer from model collapse due to recursion, right? So we have this paper which roughly says that, the language models don't perfectly capture the training distribution. You oversample from particular parts of the training distribution, and if you keep doing that, you will eventually lose fidelity. Yeah. Okay, so in AlphaGo, it's the opposite. With self-play, the model trains on itself by fighting against itself. So this is like a virtuous loop. And the reason I care about this question, it's like, what is a basis of computation or what is a basis? Like, how do we talk about these such that all of these, are sliders that you can switch, or maybe not sliders, because these, these are discrete, but like these are all slots you can fill. So how do you talk about this? What I'm certain of is that like this is not complete. And I can at least say, hey, the neural whatever is not present there. And maybe that's not interesting. Like I admit it's not that interesting, but frozen layer fine tuning, your caller is neural and your callee is neural, and you take neural inputs and you output, a probability. And your training data may vary. Because frozen layer fine tuning, that original neural network, or maybe I should say frozen model fine tuning to make it more clear that the whole model is frozen. And you add a bunch of like layers on top of the model output. You usually take like an output towards the end of the network, but not like the very final last layer. Sometimes I guess you could take it. This part of it is alchemy, but the point is, you don't know how. We haven't specified yet how this model was trained, so we need a robust type theory of these things so that we can talk about all of the state space of all of these solutions. Some of them are bound to be extremely interesting. And that's pretty much all I wanted to capture here. I'm trying to figure out how to model this. Like maybe I can even explore and see if I can use domain modeling techniques. But that's pretty much the situation I'm in. If you're still here, if any of that made sense to you, and you know anyone who might be able to help, please send this video to them. And if you can help, please, I would so very much appreciate it. And thank you so much for bearing with me as I barely scraped by in my explanation of this stuff. But hopefully this was fruitful for you, because asking these questions was very fruitful for me. Thank you so very much for listening, and have a good one.